Hi everyone. So in this video, we're going to continue talking about quadratic functions, specifically focusing on a different way of writing the equation of a quadratic function called vertex form. So in the last couple of videos, we were writing our quadratic functions in a particular form that looked like this. F of x is equal to ax squared plus bx plus c. And so this is what's usually referred to as standard form. And so what are the kind of advantages of having a quadratic function written in standard form? Well, we saw that in the last couple of videos, we saw that you can use methods from the previous videos to find the intercepts, right? The x and y intercepts. So that was, plugging in 0 for x or setting the function equal to 0. And then also we have this vertex form, vertex formula. So if your function is given to you in standard form, you know how to find those special points and use that to graph the parabola. But there's another form that can be useful that is called vertex form. And so vertex form means that instead of writing your equation kind of all expanded out like this, you would be writing it in a form that looks like this. So this is what we're going to be focusing on in this video. So I'll get a little bit more into what I mean by this, but the main advantage of vertex form is that you can use transformations. So the ideas that we know about transformations to easily identify, there's not going to be like much work to do, the vertex as well as the vertical stretch and the orientation. So orientation meaning whether the parabola is opening upward and downward. So one quick note I just want to make, and I have to scooch this down a little bit. So in your book, for some strange reason, I think almost everyone seems to agree to call this one on the left standard form and the one on the right vertex form. For some reason, I'll write this as like kind of a warning, your book calls f of x is equal to a times x minus h squared plus k. So the form that we're calling vertex form, they call that standard form. But then they just don't even have any name and, has no name for the other form, the one that I'm calling standard form. So in this class, I'll be calling the one that we learned earlier, standard form. This new form, I'll call it vertex form. Just be aware that if you look in your textbook, you might get a little confused about the language they're using. It won't really make a difference. You should be able to figure out what's going on by context, but just so you're kind of aware of that discrepancy. Okay, so we're going to talk in this video basically about how you can look at this equation and kind of pick out the vertex, vertical stretch, and orientation. But before kind of telling you all of those just as facts, I want to show you how you actually already know how to get that information. So I want to jump straight into an example. And so basically what we're going to do is we're going to use transformations to sketch the graph of f of x is equal to 2 times x minus 1 squared plus 3. Okay, so what is this a transformation of? What is our kind of basic graph that we are transforming here? Well, that would be, let's call it g of x is equal to x squared. Right, so I'm just going to go ahead and sketch that so we have that as kind of a reference as we're doing this. So this would be g of x is equal to x squared. So now we can look at this, this transformed version and basically pick out, what are all the different transformations that are happening. So for example, we can see from this 2 that there is a vertical stretch by 2. right? Because you're not multiplying x, you're multiplying the whole kind of function by 2. What else is going on here? Well, we can see that there is a shift to the right by 1, right? Because we're subtracting 1 specifically from x. And what else is going on? Well, we're adding 3 and we're adding it to the function as a whole. And so that's going to be a vertical shift, and specifically it's going to be shifting up by 3. So now we can put these together and sketch our graph. So I'm going to shift up by or actually we should do the stretch first, right? So the stretch would give us a shape that looks more like this. I'll sketch this one in blue. So the vertical stretch is going to make the graph shape more like this. So how did I get that shape, by the way? Really what you want to do is have kind of a couple of key points. So for example, normally the graph would go through 1, 1 and negative 1, 1. Now with this vertical stretch, it goes through 1, 2 and negative 1, 2. And then the other points I can't quite fit on, but the graph would also go through, instead of negative 2, 4 and 2, 4, it would go through negative 2, 8 and 2, 8. But I just can't fit those points on our grid here. And then we need to shift that graph to the right by 1 and up by 3. And so I'm going to sketch the final version in orange here. So to the right by 1 and up by 3, that means it's going to be here, and it's going to have that same shape. So it's going to be like this. So that is our final answer. Okay, so my question for you is, what is the vertex of this new function? So the vertex, remember, is this kind of point, like the lowest point in the middle here. And so the vertex for the new parabola is the point 1, 3. And what is the vertex of the original function? Well, if you just have f of x is equal to x squared, the vertex is just 0, 0. And so what's going on here is that you can basically figure out what the vertex is just by looking at the shifts, right? The horizontal and vertical shifts are what are going to tell you the vertex, right? Because if the original vertex is 0, 0, first of all, notice that stretching is not going to change that, right? If we look at this blue version, that would be if you just did a vertical stretch, the vertex is still 0, 0. Because when a point is already on the x-axis, when you stretch it, it's not going to move, right? When you multiply it by 2, it's going to stay at 0. And so the only part of the transformation that is going to change the vertex is going to be the shifts. And so together, these pieces of information, the fact that we shifted right by 1 and up by 3, that tells us that the new vertex is going to be the point 1, 3. And so what did this number 2 tell us? Well, that gave us an idea of the shape of the graph, right? It told us that it had been vertically stretched. And this is where I think it's going to be really helpful if you, rather than like having to make a table every time, if you're just kind of familiar with like the basic shape of a parabola, then you'll be able to quickly sketch the stretched version, right? If you know that on the kind of normal shape of a parabola, it goes like right 1, up 1, and left 1, up 1, right, to get these 2 points. Well, then if you stretch it by 2, instead it should go right 1, up 2, left 1, up 2, right? And that's how you'd get these points instead. If it was stretched by 3, then it would be, left 1, up 3, right 1, up 3. So just really being aware of like the shape of this part of the graph and what that's going to look like on the transform version goes a long way in being able to sketch the graph. Okay, so what did we learn here? We learned that basically if your function is written in vertex form, so I'm going to write vertex form, I'm just going to color code a couple of things here. So if we have f of x is equal to a number a times x minus some number h squared plus some other number k. What are all those different things going to tell us? Well, the vertex is going to be the point hk. And what's going on here, by the way, with this, like, why is this minus and this is plus? It's because of the fact that horizontal shifts work kind of backwards, right? And so what we saw here is that if we had x minus 1, that actually gave us a vertex x coordinate of positive 1, right? Because the shift goes to the right when you subtract. Whereas here, having a plus actually gave us still positive. And so that's why in this format, we see a subtraction within the parentheses and addition here. They could be flipped, and we'll see some examples like that. It's just that basically all you have to know is how transformations work. If you understand how horizontal and vertical transformations work, you can find the vertex. Just think about, how has the graph been shifted, and that tells you your vertex. So what else do we know? Well, the vertical stretch. So you might be tempted to say the vertical stretch is just A. I'm going to say it as the absolute value of A. And so why am I saying absolute value? Because A could be a positive or a negative number. And we'll do an example in a moment where it's negative. And so if you're trying to figure out how much the graph has been stretched, you don't want to care about if it's positive or negative. You just want it to be the positive version. So for example, if this function instead had been negative 2, it still would have a vertical stretch by 2. The only difference is it would now be facing upside down. So the positive or negative sign tells you whether the graph is opening upward or downward, but the absolute value of that number tells you how, the shape, how much it's been stretched. And so I'll describe that as orientation. So basically orientation is if that number A is positive, then you're going to have a shape that looks like this, right? It's going to be opening upward. I'm not saying it's going to look exactly like that, but it's going to be opening upward. And if your number A is negative, then you're going to have a shape where it's opening downward. Maybe I'll even write that. Opens upward. Opens downward. So again, I just want to really emphasize here that this is not like some new special formula you have to memorize. This is literally just transformations. If you understand how transformations work, you don't need to memorize anything new. But it's just kind of convenient now that we can describe this as vertex form. Okay, so I want to do a couple of examples with this. So let's use this new kind of idea to sketch the graph of f of x is equal to negative x minus 2 squared plus 3. So again, you could totally do this just using all the transformation stuff, but now that we have this new language about orientation and vertex, let's describe it in those terms. So let's start by talking about the vertex. So what is the vertex going to be in this case? And actually, let me change this because I meant to do an example where things were flipped around. Let's make this actually plus and this minus, just to make this a little more interesting. Okay, so what is the vertex going to be? Well, for the vertex, we want to look at the, sorry, I just want to change color here. We want to look at the shifts, right? And so we can tell that our graph has been shifted to the left by 2. And so therefore, the x coordinate of the vertex is negative 2. And then what about the vertical shift? Well, the graph has been shifted down by 3. And so that means that the y coordinate of the vertex is going to be negative 3. And so we can already go ahead and just put that vertex on. So our vertex is going to be negative 2, negative 3. It's going to be this point here. Okay, so next we can talk about, is there a vertical stretch? So notice that this just has a negative sign out front. That's really the same as if it was negative 1, right? And so what is our vertical stretch? Well, it's 1, which is basically none, right? Think about how stretching basically means multiplying your y coordinates by a number. If you multiply something by 1, it doesn't change. So if the number out front is either positive or negative 1, you're not going to have a vertical stretch. And so what is going to be the orientation? Well, because we have that negative sign, so basically in this case, A, that kind of front number is negative 1, right? So our orientation is it opens downward. So it should have the shape where it's going down. Okay, so now that we have our vertex and all of this other information, now we can just go ahead and sketch the graph. So again, if you're familiar with what the shape of a unstretched parabola looks like, you can just kind of fill it in, right? We know that it's going to be opening downward, and we know that it should go kind of over one, down one, right? It has that same shape as the unstretched parabola. And then, we don't have enough space on the graph, but the next point would be going over one, down three to get that kind of standard parabola shape that has not been stretched. And so that would be our graph. All right, next up, we're doing the opposite. And of course, I always forget to say this at the beginning, but hopefully you're familiar with this now because I've said it many times. I always recommend that you pause the video and try these examples yourself. Especially now that we've gotten into a handful of examples, I think you should have enough familiarity to try some of these yourself. So here we want to write an equation for the following. So let's call this function f of x. So here is f of x. So basically this is asking us to work backwards, right? So we want to figure out what is the vertex, the vertical stretch, and the orientation. And once we have those three pieces, we can use those to kind of reverse construct this formula. Okay, so what is the vertex? Well, the vertex, it looks like, is the point -2, -1. And so how do we get that vertex? Well, actually, let's write that down first, and then we'll get to the equation. Sorry, I got ahead of myself, and I wrote that down wrong. Sorry. -2, -1. Okay, so next up we have to figure out the stretch factor. So again, this comes back to being familiar with the kind of standard shape of a parabola. So looking at this one that was graphed in purple, right, before we did the stretch. So a standard parabola is going to go, depending on whether it's facing upward or downward, it's going to go like over one, up one, over one, up one, or if it's upside down, it would go over one, down one, over one, down one. But it's really just being familiar with like this shape. From there, you can always tell how much a graph has been stretched. So if we look at this graph, well, this one, instead of going over one, down one, it goes over one, down three, and over one, down three, right? So if this graph had not been stretched, it would have looked like this at the beginning, right? It would have over one, down one, over one, down one. And so if it's going instead over one, down three, that means that the stretch has been by 3. So we have a vertical stretch by 3. Finally, what is the orientation? Well, the graph opens downward. Okay, so what does this all tell us? Well, first of all, because it opens downward, we know that we should have a negative sign out front. And then to have this vertical stretch of 3, we should have a 3 out front. And so now we're going to kind of fill in the rest of this. And so if the vertex is -2, -1, well, that means that we want to make sure we're shifting left by 2, so that's x plus 2, and then down by 1, so that's -1. So that is our equation. Okay, so last thing I want to talk about in this video is how do you go from vertex form to standard form. So one thing I want to make really, really clear is that, and this is going to be especially important when we get into our next video, when we're talking about these different forms, any parabola can be written in either and both forms. I don't want you to think that that like these are two different like kinds of equations. So any parabola has actually many different ways you can write its equation. You can write it as like in factored form, right? You can write it in what we're calling standard form. You can write it in vertex form. Any parabola has many ways of writing down its equation. So for example, actually, let me kind of answer this question first, and then we'll go into an example. So if you're given a function in in vertex form, so let's say you're given this equation, and you want to rewrite it in standard form, how would you go about doing that? Well, all you have to do is kind of multiply this out and expand it, right? So you would need to multiply out x plus 2 times x plus 2, and multiply that result by -3, and then subtract 1, and just combine all your like terms. So that is going to be our general method. So to answer this question, we want to, maybe I'll say it this way, expand and simplify, basically combine your like terms. So for example, let's say that we have an equation in vertex form that is -3 times x plus, oops, that's not what I wanted. That's the other example. 2 times x plus 1 plus 5, squared. So the first thing I want to do is I want to rewrite f of x in standard form. Okay, so let's go and do that. So how would we do this? Well, we would just take our equation, so we have 2 times x plus 1 squared plus 5, and we would just multiply everything out. So when you're multiplying something like this, where we have the 2 on the outside and then x plus 1 squared, we want to start by multiplying together x plus 1 times x plus 1, and then we can multiply that entire result by 2. So we have this. Okay, so what is x plus 1 times x plus 1? Well, that would give us x squared plus 2x plus 1. And so now we can distribute in this 2, and we would get 2x squared plus 4x plus 2, and then we still have plus 5. And so now we can combine all of our like terms, and we get 2x squared plus 4x plus 7. So this would be the exact same parabola in standard form. And if you go into Desmos, you'll actually see, if you graph these two parabolas, you'll see the exact same thing. And I'll show you that at the end. I really want you to understand that we didn't do some magic here. All we did is we took this equation and we just wrote it a different way. So truly, the one that's circled in purple and the one that we just found in blue, that is the same parabola. It's just written in two different ways. Okay, so now before we look at the graph, to really kind of convince you that these are the same exact parabola, I want to verify that both forms give you the same vertex and the same y-intercept. We're not going to do x-intercept just because it's so much easier to find the x-intercept when it's in standard form. That I just don't feel like it's really worth doing it from vertex form, but I do want to show that the vertex and the y-intercept are the same. Okay, so let's start with the vertex. Actually, let me do this in a different color. Okay, so for the vertex, with our first one, so the original form it was given to us in was 2 times x plus 1 squared plus 5. So how do we find the vertex in this form? Well, we can just read it off, right? We can just think about vertex form. And so we can see that this graph has been shifted to the left by 1. And so the x-coordinate of the vertex is -1. And then we can also see that the graph has been shifted up by 5. So the y-coordinate of the vertex is 5. So now let's do it from the other form. So the other form we had was 2x squared plus 4x plus 7. So here we have to remember our other method for finding the vertex. So the other method for finding the vertex was -b over 2a. Right, so -b over 2a, in this case, would be -4 over 2 times 2. And so that is -4 over 4, which is -1. And then how would we find the y-coordinate of the vertex? Well, we just plug it in. So we would have 2 times -1 squared plus 4 times -1 plus 7. And so that's going to give us 2 times 1 minus 4 plus 7. So that is 2 minus 4, which is -2, plus 7, which is 5. And so what did we get for the vertex? We get -1, 5. And so if we compare what we got in both methods, we got the exact same thing. So we're good. We got the same vertex. That kind of suggests to us that this is actually the same graph. Okay, what about the y-intercept? So again, I'm going to start by writing down the vertex form that was originally given to us. Okay, so I'm actually going to make a mistake, and I want you to think about why is this a mistake. So looking at this vertex form, well, remember from the earlier video that number at the end is our y-intercept. So according to that reasoning, the y-intercept should be the 0.05. So I want you to pause and think about why is that wrong, and how could you check whether that was correct or not? So the issue is that the only reason, so it is true that when your equation is written in standard form, so when it looks like this, it is true that this last number is going to be the y-intercept. But if you remember, I told you not to just memorize that as a fact, but to remember that the way that you can always find the y-intercept is by plugging in 0 for x, right? Because if you think about what it looks like on the graph, the y-intercept always has 0 as its x coordinate. And so if you plug in 0 for x, you're not going to get 5 here. The only reason that you get the last number when it's in standard form is because when you plug in 0, this turns to 0, this turns to 0, and you're left with this number. So it's a really common mistake I see students make is that they just memorize, oh, it's just the last number. But that's not true when your function's in vertex form. So let's actually see what happens when we plug in 0. So if we plug in 0, we would get 2 times 0 plus 1 squared plus 5. And so that's going to be equal to 2 times 1 squared. And so 1 squared is just 1, so we have 2 times 1. And so that's equal to 7. And so that tells us that the y-intercept is 0, 7. And then we can see the same thing, we get the same result if we use the standard form. So in standard form, we had 2x squared plus 4x plus 7. So in this case, if we plug in 0, what happens is that we get 2 times 0 squared plus 4 times 0 plus 7. And so in this case, the first two terms just become 0, and we're left with 7. And so that's why when it's in standard form, it is true that it's just that last number. But again, rather than memorize that as a rule and risk getting mixed up, just remember that you just plug in 0 for x. It doesn't take that long to plug 0 in to any form, really. So we got the same point either way. So last thing I want to do, just to really convince you that these are truly the same graph, I just want to show you in Desmos that if you graph both the vertex form and the standard form, they're literally the same exact parabola. So here in Desmos, I have graphed currently the vertex form, 2 times x plus 1 squared plus 5. We can see, as we expected, we have a vertex of -1, 5 and a y-intercept of 0, 7. And so now in blue is going to show up the standard form that we found. Oops, let me do that. So we can see this is the standard form, this is the vertex form. They are the exact same function. So actually I lied. There's one more thing I just want to quickly mention as kind of a preview for the next video. So we learned how in this example, we started off right with vertex form and we just expanded it to write it in standard form. So what about the other way? So the other question we can ask is, how do you go from standard form to vertex form? So it turns out that that is going to be a harder process, and that's actually what the entire next video is going to be devoted to. So vertex form to standard form is pretty easy because all you have to do is just multiply stuff out and kind of expand it, right? Break it down. Going the other way is going to be kind of a little bit of reverse engineering. It's going to take a little bit more kind of cleverness. And so this is going to be a method called completing the square. And so this is what we're going to be covering in our next video, but I just wanted to mention it because I think it's really important to understand the context of why we're going to talk about completing the square. So I want you to think of completing the square when we get into it in the next video as just the reverse of what we talked about here. It's the reverse of expanding something and rewriting it in standard form. It's going to be kind of working backwards to figure out how to write it in this special vertex form. All right, I'll see you all in the next video.